Okay, so welcome to the first lecture for Physical Biochemistry, bmb540. My name is Himanshu Khandelia, and my job will be to talk about the physical chemistry principles of this course. So, physical chemistry or basic thermodynamics is essentially the study of energy transfer, which could be in the form of heat, work, or internal energy, and some other things which you will encounter during the course during chemical and physical transformations of systems. By chemical transformation, we could have an enzymatic reaction. By physical transformation, you could have a change of phases, such as the unfolding of a protein. A system could be anything. It could be an entire cell. It could be the human body. It could be an ideal gas inside a piston, or it could be a protein attached to a ligand. Here is the list of topics that I will cover during this course. Um, I will not go into each of these right away, but in this lecture we will talk about ideal gases and kinetic theory. Um, but the first question that should arise in your mind is why you as biomedicine or BMB students need to know physical chemistry. Um, there are various questions that can be answered quantitatively if you understand the basics of physical chemistry. So here I will show you a small movie showing you two lipid species, one in orange and the other in green, surrounded by blue water, which will spontaneously self-assemble into a lipid membrane. So here you can see that the system spontaneously assembled into a two-dimensional lipid membrane. So why does a lipid mixture assemble into a bilayer? Why can't the lipids be dissolved in water? Why can't they form a micelle instead? Will they still form a bilayer at a higher temperature or at a lower temperature? Such questions can be answered if you understand the principles of physical chemistry. Here is another example which is closer to biology. On the right hand side is a simulation animation of the binding of a potassium ion onto the ion binding site of the sodium potassium pump. Here you can see the first ion bound and then you can see the second ion bound. I will play this movie again. So what you see is a dynamically moving protein and ions surrounding it, and eventually a couple of these ions find the ion binding site and they bind to this ion binding site. Can we calculate the energetics of this ion binding? Why does the potassium ion bind and not a sodium ion, which is also present in the surrounding media? Can we design drugs that can eliminate these bindings? And what should we calculate if we want to differentiate the binding of sodium versus potassium to this protein? So these questions and many others can be answered after you understand the basic principles of physical chemistry. Here are some more fundamental questions. We all know that ATP is used as an energy currency in the cell, but why ATP and why not other molecules? How much energy can be used by a cell when it oxidizes a single molecules of glucose by the glycolysis and citric acid cycles? Why are there so many steps involved? Why do you need NADH or NAD plus and so on? A more fundamental question, if you put a ball on the ground, why does it not spontaneously jump? It might sound ridiculous, but it is possible. Similarly, if you take a few drops of ink and put them in a beaker of water, this ink dissolves in water. What makes the ink dissolve in water, and why doesn't ink spontaneously separate from water? So these are some of the questions that you can address using physical chemistry. There is no doubt that this is one of the more difficult courses that you will encounter during your education here. And I would like to suggest three important strategies that you should keep in mind throughout the course. The first is to think about a molecular level interpretation of every equation and every phenomenon that we discuss in this course. Secondly, you will be encountering several new terms which you haven't seen before. You may have seen entropy, for example, but you will also encounter enthalpy, heat capacities, activity coefficients, and things like this. So you should ask yourself, why do we need this new term? Is the instructor just going to make my life difficult? Or is there some logical reason behind using these terms? And finally, and this is true for all equations in fact, try to speak your equations in terms, in words. So what you see below is the ideal gas law. You would say PV equals nRT. I would rather say the pressure of an ideal gas multiplied by its volume is equal to the number of moles of the gas multiplied by the gas constant multiplied by the temperature. The more you speak your equations in words, the better it will be for your exam and your learning. Okay, so with that, let's get to business. We will first talk about ideal gases. And the ideal gas law, which you just saw in the previous slide, is derived from the kinetic theory of gases, which states that atoms inside an ideal gas undergo incessant collisions. For an ideal gas, we assume that all these atoms have the same mass. They're all very small particles and the motions are completely random. The only interactions between these particles in an ideal gas are the collisions between them. In order to derive the ideal gas law, we need to define the pressure and the temperature. Now, the source of pressure in a gas or a liquid confined in a container like the one here is the collisions, the constant collisions of the particles of the gas with the walls of the container. Using the kinetic theory of gases, it can be shown that the pressure, which is equal to the force exerted on the wall divided by the area, is equal to 2 divided by 3 times the volume of the container multiplied by the total kinetic energy of all the particles inside the container. Similarly, the source of temperature is the constant molecular motion of the gas particles, and it can be shown that this temperature is equal to 2 divided by 3 multiplied by the number of particles n in the container multiplied by the Boltzmann constant, which we will come back to, multiplied by the total kinetic energy. So from equation 1 and equation 2, one can eliminate the kinetic energy, and then one obtains the equation where pressure is equal to the number of particles multiplied by the Boltzmann constant multiplied by the temperature divided by the volume. The number of particles is equal to the number of moles multiplied by Avogadro's number. And then this product of Avogadro's number multiplied by the Boltzmann constant is equal to the gas constant R. And here is the value of Boltzmann constant. Boltzmann constant multiplied by temperature is the measure of the thermal energy of a system, and we will talk about that later again. So what you get out of all of this is that pressure is equal to the number of moles multiplied by the gas constant multiplied by temperature, or at constant temperature, the product of pressure and volume is constant. The units of pressure are Newton per meter square or pascals. The value of atmospheric pressure, which you are now feeling, is equal to this value, about 100,000 pascals, and this is also equal to 1.0325 bars, where 1 bar is equal to 10 to the power of 5 pascals. Here is one exercise you should take up, is to derive the units of R in terms of energy. So for this, you need to write pressure in terms of Newton per meter square, volume in terms of metric cubed, N in terms of moles, and T in terms of Kelvin. And then you can derive the units of R in terms of energy. Okay, so if I look at this equation here, PV equals nRT, and I keep the temperature constant, then the equation I get is PV equals constant. So if I make a pressure versus volume plot, at a given temperature, the pressure versus volume must be hyperbolic because PV equals constant, and it looks something like this. As you increase the temperature, the product between pressure and volume rises, and the curve goes in this direction. And of course, at any given point, the product between the pressure and volume is the area under the curve, and this is equal to nR multiplied by T. Similarly, you can plot pressure versus 1 by volume, and then you get straight lines with increasing temperature. As I noted earlier, the universal gas constant is Avogadro's number multiplied by Boltzmann constant. At constant temperature, if a system is being taken from point 1 to point 2 at constant temperature, then P1 V1 equals P2 V2 because the temperature hasn't changed. You can derive this very easily. This is called Boyle's law. If on the other hand the pressure is kept constant, then V1 by T1 equals V2 by T2. This also can be derived fairly easily, and I will refer you to sections in the book that discuss this. Finally, we will talk a little bit about mixtures of gases. So far we have talked about a single ideal gas, but you can have a mixture of gases. And we will define a quantity called the partial pressure. So the partial pressure of any gas J is defined as the product between the total pressure of the mixture of the gas and the mole fraction of the gas J. The mole fraction is the number of moles of gas J divided by the total number of moles in the system. It follows that if you add up individual pressures, you get the total pressure. Individual partial pressures, you get the total pressure of the system. So here is a simple exercise on mole fractions. Air has about 20% oxygen and 80% nitrogen. So what are their mole fractions? If we assume that there are 100 moles of air, there will be 20 moles of oxygen and 80 moles of nitrogen. So the mole fraction of oxygen is 20, the number of moles of oxygen divided by the total number of moles, and this is 0.2. Similarly, the mole fraction of nitrogen is 80 divided by 100 and 0.8. And the sum of these two is always equal to 1. So the partial pressure of oxygen will be 0.2 multiplied by the total pressure. Okay, so there used to be a poll which I cannot conduct this semester, but here is a question you should think about. What is an ideal gas? Where there are no bonds between atoms, the gas whose temperature is 0 Kelvin, or where atoms do not interact with each other than colliding. And these are plots that I already showed you. And in the next part of the first lecture, we will look at the first law of thermodynamics.